Right? So constraint optimization at the word suggests is optimization in the face of a constraint. Like we were discussing, let's say that you are still on a mountain slopes, but now you're not allowed to look for just the peaks. You have to look the highest point along a certain plane. Okay? All right, so another example could be, let's say you have an apple, and you're looking for the point to the extreme right. Okay? So obviously that would be this point, right? But now you suddenly change yourself and you say, no, you have to look at the point on the extreme right on a certain plane. Because if you have to be on the plane and to the extreme right, you can see automatically the point becomes that, right? Now, of course, it's a 2D picture. Actually, in 3D, it might be somewhere else. But you get the idea, right? The constraint optimization is you don't look for global maxima and minima anymore. You look for maxima and minima along points that satisfy that constraint. And then we talked about how we can think of that graphically. And we said that graphically, if you think of a 2D problem where you have, let's say, a certain constraint, g equals to 0, and then certain level curves of constant f, the optima occurs when these two have the same slope. That means minus gy over gx equals to minus fy over fx, or equivalently gy over fy equals to minus fy gy over fy equals to gx over fx, and we said this is also equal to what we call Lagrange multiplier lambda. Okay? Oh yeah, it should actually be the, usually it's the reverse way, so let's just stick to that. Usually say f plus lambda, yeah. So you can write it as fy over gy equals to minus and equals to 1. Okay? All right, so, and then I did an example using this approach. But now, most complex problems in life, not necessarily two-variable problems, okay? So now let's try to figure out how we're going to apply this concept of Lagrange multiplier to solve more complex problems. So now let's say that we want to solve a general problem where you have f, which is a function of, let's say, unknowns. And the unknowns, let's say, is x1, x2, x3, x4, x5, could be any number of unknowns. Okay? This is our objective function. Okay? And the constraints could be gi, it's a gain function of x, equals to 0. Where I goes from 1 to n. So let's say there is not just one constraint, but n constraints. And the objective function doesn't depend on just one or two variables, it depends on multiple variables. Yeah?
For like a number of x, you're going to need a certain number of constraints, right? Like if you had 3 variables, you're going to need 2 constraints.
No.
You have, really?
You can do it without any constraint. You never need constraints.
But wouldn't you not get?
But you cannot have any more than how many constraints? If you are looking at a problem of 3 unknowns, what's the maximum number of constraints you can have? 3. And if you do have 3 constraints, is it an optimization problem?
No.
No. What is it now?
It's just a point.
So it's a root finding problem, right? But you can always have 0 constraints. There's no minimum limit of constraints. You can always look for a maximum without any constraint. That's unconstrained optimization.
With your maximum, like say you had 3 variables and you had, I don't know, I'm trying to get a question, but like
Yeah, so let's say there are 3 variables with no constraints. So let's say there's f is a function of x1, x2, x3 with no constraints. How are you going to optimize it? You have 3 unknowns, what will be the 3 equations?
Mass balance.
Mass balance?
What? That's all I know how to do. Start with the mass and then you do energy.
What was the question? I'm sorry.
The question is, he's asking if there are 3 unknowns, how can you optimize? I'm just asking, how will you optimize f is a function of 3 unknowns?
You just
What?
do Newton-Raphson method.
The rational?
Or no, not, oh, that's never mind.
Yeah, the 3 equations will be fx1 equals to 0, fx2 equals to 0, fx3 equals to 0. So all those 3 equations simultaneously, 3 unknowns, 3 equations, you're done. Now, of course, to figure out there's a maximum and a minima, you have to calculate all the derivative business. But it's straightforward, unconstrained. So you do not need constraints. You can always optimize without any constraints. Right? But, so there is no limit on the minimum number of constraints. There could be, there could be 0 constraints. But there's a limit on the maximum. The maximum constraints, at least the maximum equality constraint, cannot exceed the number of unknowns. And if it equals the number of unknowns, it's no longer an optimization problem, it's just a root finding problem. Okay, but in principle, it's still feasible. All right. So now this obviously is a very complex problem. We're not going to actually solve any problem like that, but I'm going to explain to you how to solve it. So first, I will just kind of tell you something which may seem magical. So what I do is I define a new function called f bar. Okay? And I'm going to define f bar as the actual function f, okay, plus lambda I gi. Okay. Now you may say, what is this? And then summation. So originally f is a function of, let's say the size of is, let's say there are k unknowns. Okay, k unknowns. So f is a function of k unknowns, right? Now the way we have defined this f bar becomes a function of how many unknowns? There are all those k unknowns, plus we have introduced these new unknowns called Lagrange multipliers. All these lambda i's are what are called Lagrange multipliers. Okay? Let me write it out more explicitly so you'll see. So let's say it's f plus lambda 1 g1 plus lambda 2 g2 plus dot 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 dot.
So it's k plus n equal to the number of unknowns.
No, so the number of unknowns are equal to now k plus n, right? So now the number of unknowns is k plus n. But I'm going to tell you something and you just have to take my word for it and then I'll prove it. Okay? So my assertion is that by defining f bar in this particular manner, I have converted my problem for constraint optimization to an unconstrained optimization. So my assertion is that if you maximize f bar without any constraint, you will get the same solution as what you are looking for. And let me try to explain why that is the case. So you know that if you're trying to maximize f bar subject to without any constraint, our equations always are the derivative of f bar with respect to all unknowns equals to 0, right? So if you take the derivative of f bar with respect to lambda 1, what do you get? So del f bar, del lambda 1 equals to what? From this equation? G1, right? And that equals to 0. And you can see that is our constraint. So you can see by rewriting this function f bar in this particular way, the constraints get inbuilt into the optimization process, and your constraint problem basically becomes an unconstrained problem. Does that make sense? At least mathematically, does it make sense? You can see that, right? That all the derivatives with respect to all the lambdas give you the constraints back. That means if you optimize this problem, wherever the optimum solution is, all the constraints will automatically be satisfied, right? Because at the optimum, all the g's will be 0. Make sense? And so you already know how to do an unconstrained optimization. So you can see, so that's the beauty of Lagrange multipliers. That constraint optimization is weird, right? If you think about it, you have to optimize, but along certain constraints. You have to cut. It's very difficult to postulated mathematically by doing this trick. You basically posed your problem as an unconstrained optimization, which is just easier to solve usually. Okay, does it make sense to everybody? Any questions? We're going to do an example. Hopefully that will help things out a little bit. Yeah.
Do you know if the Lagrange figures that out by like some mathematical proof, or did you just kind of like figure it out by guessing? Oh, if I add them up like this.
I don't know.
Do you know how we figured it out? Actually, is what I'm asking.
I don't know. I can come up with a story if you want. Like to hear it? Actually, it wasn't Lagrange who came up with this. I'm just kidding. I have no idea. All right. No, actually, I'm pretty sure that he kind of backed this out in how to write this in this way. Okay, all right. So let's do an example, and as I said, that might help you figure this out. Okay, shh. So we're going to do two examples. One will be an example, well, they both are sort of chemical engineering example, but one will be more chemical engineering than the other one. So the first example we'll do is, imagine that you have a cylinder, okay, and the volume of the cylinder is fixed, and you want to minimize the surface area. Okay? All right, so the volume is fixed. That means the volume V equals to pi r squared h. This is fixed. So what are the two unknowns for this problem?
Surface area.
R and h, right? Surface area is the function that has been minimized. The unknowns are R and h. Okay, so V equals to pi r squared, which is a constraint. So how are we going to write this constraint? We always like writing constraint in a certain way. G equals to 0. So what is G?
V.
V minus that is equal to
V minus pi r squared h. We can always solve, we can always eliminate, but that's not what we're trying to do.